So in this video, we're going to use the alternating series test in a specific example. So just a reminder, the alternating series test said that if we have an alternating series of the form -1 to the n plus 1 times bn, where the bn terms are positive, then all you need to check is that the sequence bn's is decreasing and that the limit is 0. With those two things, it's enough to show to conclude that the series is going to converge. We proved that. We proved that in another video, and you can look it up. So now what I want to use is use that in this example I have here. So I'm going to use that. This example where my bn is n factorial over n to the n, and I have the alternating term here, n-1 to n plus 1. So okay, so all we have to do according to this the test we just saw is that we have to check two things. We need to check that that the sequence bn is decreasing, and two, that the limit of the bn's is 0. If we check those two things, we're done. Okay. Okay. So how do we check that it's decreasing? Well, we're going to do in the order which is the more practical way to do it, and in practice. But then the logical way is kind of like backwards. So I'm going to start with a statement that I want to prove. I want to prove that I want to compare the term bn with bn plus 1. Right? I want it to be decreasing, so I want this term to be smaller. Right? I want the bn plus 1 to be smaller. So I don't know if this is true, but let me just write it down. So if this was true, what I would have is that the n factorial over n to the n term would be bigger than the n plus 1 factorial divided by n plus 1 to the power of n plus 1, correct? Okay, I don't know if this is true. Okay, I'm following the logic here. So if this was true, then what I could have done is I could have multiplied the n plus 1 on this side and divide by the n factorial on that side. So I would have something like this, right? And now what I'm going to do is, now the important thing is on this side, so I don't know if this is true, but the important thing is on this term right here. Let me change colors here to grab this point. We've probably used this already, but n plus 1 factorial, remember that it is nothing else but n plus 1 times n factorial, right? So if I have that divided by n factorial, I can really just cancel the n factorial. This is n plus 1. So this term that I have here is really just n plus 1 term, right? So continuing with my argument over here, this becomes n plus 1 to n plus 1 would be bigger than n plus 1, and this n to the n down here, I'm going to put it over here. So again, all this, I don't know if it's true, okay? But if it was, then I'm going to write one more thing here. 1 plus 1 to the n plus 1. On the right side, I can distribute this, and I'll have n to the power of n plus 1 and plus an n to the n. So there you go. I don't know if this is true, but this last thing I wrote is easy to see that's true, because we probably have some experience expanding these binomials to the powers. And remember that every time you have a binomial to a power, the first term that shows up is this. Then I'm going to have a coefficient times this to the n, so 1 power less than the power, and then 1 to the 1, but doesn't matter. In any case, I'm going to have more terms, n to the n minus 1, with another coefficient, and so on. These two terms that I have here is at least these two terms, right? This whatever's inside this box, this coefficient would make this term even bigger. I'm going to add a bunch of terms over here. So for sure, this term on the right is bigger than only the first two terms. Where are these two? So this is true, and this is again, like I said, a little backwards logic, but we started writing something that we want to know is true, right? Let me highlight that. Isn't that what we want to know is true? We said that statement would have been true if this was true. That would have been true if this was true. And when I finally get to a point where, oh, but this guy I know is true, so then you can really go backwards. So this is true, then this is true, then that's true, so we know this is true. And we're done. Okay. So we did prove that it's decreasing, and that part is done. Okay, so now let's go down to, so in this part we checked it's decreasing, and we are done with that part. And let's try to check that the limit actually is 0. To check that the limit actually is 0, it's also not very hard. So I'm talking about the sequence bn's. Oh, I'll change color, sorry. We're talking about the sequence bn, which I know they're positive terms, okay? Bn, they're positive terms. And it's also, I'm going to write it down, it's really equal to have n to the n over n to the n. Sorry, n factorial n to n. And now I want to bound this by saying, well, let's write this down. So this guy is really, I'm going to write him, the factorial is 1 times 2 times 3 times 4 all the way to n, right? And the denominator has n to the n, so I can write 1 factor of n for each one of these terms, right? This is exactly what n to the n factorial divided by n to the n is. Okay. But now, just look at the first term. This first term is 1 over n. So I can compare this with 1 over n. And all these terms over here are less than or equal to 0. Then 1, sorry. Less than, well, the last one is 1. So if you forget about that one, the product of all these guys is less than 1. So for sure, this is less than 1 over n, right? So just to put it in one line, I just told you that the bn is sandwiched between 1 over n and 0. Okay, you know that the limit when n goes to infinity of 1 over n is 0, so using the squeeze term or sandwich term, the limit of the n of the bn's is also 0. Squeeze term. Okay, so there we go. We did prove that the limit is, that the limit is 0 and that it's bounded, that it's decreasing, so we're done. We know that the series converges. Okay. Okay. Something else we saw in the afternoon series was this other result. Let me go back, sorry. We saw this thing right here. The remainder was less than the n plus 1 term. So that's a very simple idea, and it's a very easy way to estimate the sums. So now I'm going to use that to estimate very quickly this sum using S5, which means adding the first 5 terms. So if I do that, what we're going to get is first I'm going to write, well, S5, and just add a 1 minus 2 factorial over 2 squared. So I'm going to write them down here just because I have, so 3 factorial is 6, 3 to the 3 is 27, then it's a minus 4 factorial is 24, and 4 to the 4 is 256, and the last one is 125 factorial divided by 3125 is 5 to the 5. So you put this in the calculator, and it gives you a 0.6669. Now, something important is that we know, because of the picture I showed you before, the last term is a positive, so this is an overestimate, right? Because you're adding and subtracting, so if you end up adding, the next term you're going to subtract, so this is an overestimate. Okay, so this is the estimate, but what is the estimated remainder? Well, my remainder of the fifth term is smaller than the next term, always. So all I need to do is find who is the next term, which is 6 factorial over 6 to the 6. And that calculator is 0.154 if I use 4 decimals. Okay? So this is an easy way to estimate using 5 terms, and this would be my estimate the remainder. Okay, so I know the real value is between this and this minus that, right? Because this value is our estimate. Okay, so this is a quick way to find estimates for oscillating series. I'll make more examples and more videos.